Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. My topic for this evening will be a continuation of my long video format topic, DC circuit. This will now be the heart and soul of DC circuit. If series circuit is an easy one, and so with the parallel circuit, the combination of a series and parallel, like what I said, it's the heart and soul of this circuit. Okay, let's proceed. My topic for this evening will be long video format, direct current circuit lesson number 6, and the title of the topic will be example problem on the so-called series parallel connection. We are now through with the concept of series circuit, and we are now through with the concept of parallel circuit. So for this evening, I will be presenting a problem that is a combination of a series parallel connection. Because a series parallel connection is actually more complicated than the series, and so with the parallel. So for tonight, like what I said, series parallel connection is actually the heart and soul of a direct current circuit. Okay, let's proceed. I've given you a problem here. The figure will be this one. Oh, I give you a connection, series parallel connection. And the total number of resistances involved is actually 7. This is 1, 2, 3, 4, 5, 6, and 7. The subscript refers to the number of the resistances. So R1 will be 1 ohm, R sub 2 will be 2 ohms, R sub 3 subscript, right, is 3 ohms, R sub 4 is 4 ohms, this portion here, R sub 5 is 5 ohms, R sub 6 is 6 ohms, and R sub 7 is 7 ohms. The applied voltage is a battery, and the voltage of the battery is 24 volts. So this should be the plus terminal, and this should be the negative terminal. The problem is just asking what will be R total equal to. R total meaning the total resistance of the entire circuit. If we try to compress all the resistances as a single equivalent resistance, what will be R total equal to? Then after that, what will be capital letter I with the subscript T, meaning the total current? There are only 2 requirements, but since the connection is a series parallel connection, it's not an easy one, right? So we will be applying our knowledge of the series concept and parallel concept. Okay, let's proceed. For the solution, to compute for the single equivalent resistance of this, single equivalent meaning if we get our multitester, okay, if we try to measure the resistance across this terminal here, okay, the problem is asking what will be R total equal to. Okay, this is my multitester. I just brought out the test leads. Okay, so to do that, we will be using our knowledge of the concept of series concept and parallel concept. So it will be, the solution will be something like this. We will be starting at the far end on this portion here. Okay? Because if we try to disconnect at this location here, we try to disconnect. And so with this. Okay? And if we try to get our voltmeter, we tap it here. No, not voltmeter, multitester. Then we set it to the ohms rating. What we will be getting will be the ohmage at this terminal here. And theoretically, okay, what will be coming out on the multitester we could solve it theoretically. That's why I try to disconnect it here. Okay? And we will be asking ourselves, what is the connection of R sub 6 and R sub 7? What do you think, guys? I think the connection between R6 and R sub 7 is actually they are in parallel. Why? Because if we try to get our voltmeter here, the voltage across R sub 6 will be equal to the voltage across R sub 7. And for a parallel connection, okay, the voltage should be the same. So if they are the same, they are in parallel. Okay? So for us to take the single equivalent of R sub 6 and R sub 7, like what I said in the concept of parallel connection, if there are only two resistances in parallel, to take the single equivalent, it will be their product all over the sum. So if we try to take the single equivalent of this, okay, in which I represent that as RE with the subscript 1, meaning equivalent resistance number 1. This portion here, the single equivalent of R6 and R sub 7, I represent that as RE1. Since there are only two, it will be the product all over the sum. We are given 6 and 7, so they should be 6 and 7 all over the sum, which is 6 plus 7. So that will be 42 over 13. And the single equivalent will be 3.23 ohms. Okay, guys? So the single equivalent of R6 and R sub 7, since they are in parallel, it should just be only 3.23 ohms. Okay, so you will not get confused. I will try to remove already the R6 and R sub 7. Then I will try to replace that one by its equivalent. So I will try to erase this one. Okay? And we know the single equivalent already, right? This is RE1. The single equivalent of R sub 6 and R sub 7. And this is actually 3.23 ohms. Right? What's the next procedure? Okay? I will try to disconnect here. Okay? We'll try to disconnect. And if we try to get our multitester, if we try to measure the resistance across this after the disconnection, obviously this R sub 3 here is in parallel with RE sub 1. The current should be common to both, right? The current should be common. That's the common current. Okay? After the disconnection, for the meantime, R3 and the single equivalent of R6 and R sub 7 is actually the current should be common. So if the current is common, they are in series. Right? So to take the single equivalent of this one, okay, single equivalent, I represent that by RE with the subscript 2, meaning equivalent resistance number 2. The single equivalent of RE1 and R sub 3. Since they are in series, okay, it will be the sum. So RE2 now will be the single equivalent of R6 and R sub 7, which we erased it already, plus this R sub 3 here. So RE with the subscript 2 will be 3.23, the one we computed, plus 3, right? And the value is 6.23 ohms. Okay? Since we know the single equivalent of R3 and this RE1 now, we can proceed to erase them, right? We'll put the computed value RE2. Okay? We erase it again. We know the single equivalent already. That's R sub 5, right? This is the single equivalent. This is now RE2. And RE2 is actually, as per our computation, 6.23 ohms. Okay? We can erase R sub 3 now. Okay? We use the value already, right? So we are making the circuit simpler now as we move from right to left. And again, we disconnect it here. Okay? Then we'll get our multi-tester. Again, we measure the resistance across this. Obviously, this R sub 5 is in parallel with RE sub 2, the one we computed. They are in parallel. Right? So they are in parallel. This RE2 is in parallel with R sub 5. So RE sub 3 now, if we try to take the single equivalent of this, we represent that by RE3. It should be the product RE2 R5 over the sum RE2 plus R5. They are in parallel, right? Okay? So we are just using the concept of parallel circuit. So substituting values, this should be 6.23 times 5. This is 5 ohms. All over 6.23 plus 5. This is 31.15 or all over 11.23. What comes out for RE3 will be 2.7738 ohms. Meaning the single equivalent of this one will be 2.778 ohms. So actually we can now erase this one. So the circuit is becoming simpler, right? And we put RE3 here. This is RE3. And the value is 2.7738 ohms. Okay? So again, to simplify the circuit, okay, we disconnect it here. Okay? Then try to get the multi-tester again. Then try to measure the voltage across this. Or not voltage, the resistance rather. Okay? Obviously, this R sub 2 is in series with RE sub 3 because the current is common, right? That's the common current. So if we try to take the single equivalent of that one, I represent that by RE sub 4. Since they are in series, it will be the sum RE sub 3 plus R sub 2. So this should be 2.7738 plus 2. 2.7738 plus 2. And the single equivalent is 4.7738 ohms. Okay? So we now know the single equivalent of R sub 2 and this. So we can proceed to erase this one now. Okay? We replace it by its single equivalent RE sub 4. So this is RE sub 4. This is RE sub 4. And as per our computation, it is 4.7, oh sorry for that one, 4.7738 ohms. Right? And again, to take this next step, we try to disconnect it here. Okay? Then try to take your multi-tester, try to measure the resistance across this. And what will be the connection of R sub 4 and RE sub 4? They are in parallel, right? So we can take the single equivalent since they are in parallel, right? We will be using the product all over the sum, right? So we are given RE sub 4, 4.7738 times 4, they are in parallel, all over 4.7738 plus 4. This is 19.052 over 8.7738. The single equivalent is 2.1764 ohms. So actually, the single equivalent of R sub 4 and R sub 4, which is represented by RE sub 5, we can erase this one now. right? And we'll place RE sub 5. This is RE sub 5, and the value is actually 2.1764 ohms. And again, if we try to disconnect it here, we disconnect the power source, right? This will be an open terminal. If you try to get your multitester, you tap it here, you set it to the ohms rating. What you will be getting will be the total resistance of the entire circuit after the simplification. And as you can see it, this R1 here is in series with RE sub 5. They are in series, right? That will be the circulating current. Since they are in series, the single equivalent of R sub 1 plus RE sub 5 now represents R total. So R total here is RE sub 5 plus R sub 1, since the connection is in series. And the summation of RE sub 5 plus R sub 1 is actually R total, the single equivalent resistance of the entire circuit. If we try to simplify, or substitute rather, this should be 2.1764 plus 1. And the single equivalent resistance of the entire circuit, which is a combination of series parallel connection, it will be 3.1764 ohms. That's the single equivalent of the complicated original circuit after compressing it. That's a single equivalent resistance. So if we try to compute for the total current, okay, that's an easy one now. Actually, we can erase again these two here. And what will come out will just be simply a series circuit like this. Right? This is R total. And as per our computation, the value is 3.1764 ohms. Okay? That's the total resistance of the entire circuit, the one on the right. So if we try to reconnect the power source, series circuit, right? We are given the voltage source, we are given total resistance. So what will come out here is I total. And using the equation voltage equal to IR, current now will be voltage over R. And in here, voltage over R, the total voltage of the entire circuit is 24 volts. The total resistance, single equivalent resistance of the series parallel combination is 3.1764. The total current is 7.561 amperes. Okay, that's it, guys. That's how we compute problems involving series parallel connection. Okay, like what you say, if you are on the series portion, apply your knowledge of the series concept. If you are on the parallel connection, use the concept of parallel connection. Okay, good evening from Los Angeles. This is Professor David J.